Dr. Roldan. So he'll talk about colloidal heat engines.
Thank you very much, everyone, for the invitation. It's really a pleasure to be here for the first time. I'm really honored to have this crowd in front of me. I think it's the biggest crowd I've had in a long time. So today's lecture is entitled Colloidal Heat Engines, Passive and Active. It's a bit of an overview talk, but I thought that this morning we would get a lot of theoretical insights, and indeed, I think the lecture were great and the introduction. So all that was explained by Abhishek and Luca is valid also for my lectures. So this is the general basic formalism of stochastic thermodynamics. But today, to give you a bit of motivation, I'll discuss more on applications. So my course will be more on applications of biology, which is the central topic of this school. But today will be more applications on engines, and especially in experiments. So I'm a theorist, but I've worked a long time as experimentalist, and to me, it's one of the most beautiful parts of stochastic thermodynamics, which is the connection between theory and experiment. Before starting, this is a tentative schedule. So you will see that my course and the course by Arnab, which is here, is a joint course together with him. And it's really an honor to work with him because he's one of the pioneers of stochastic thermodynamics in India. Also with Abhishek and with Roldan, his picture when he received the ICTT prize. So it's really an honor. And what you see here is a bit the structure. So we have divided our lectures in two courses. One on active heat engines, which first lecture is the one I'm giving today, this L1. And the other part is on irreversibility and dissipation in biology. So these are direct applications of theoretical concepts, stochastic thermodynamics in biology. You see a bit the structure is a bit chaotic because I'm going to give the first lecture on active heat engines. So it's the introduction to what Arnab will discuss on Thursday and Friday. And Arnab will give the introduction to my lectures on irreversibility and dissipation in biological systems. So please take a picture of this because I think Arnab will repeat this scheme here. Okay. As a brief introduction, I'm working in Trieste. Trieste is a city in the Adriatic coast in Italy. This is our campus. It's not as tropical, beautiful as here, but we have the sea, which is really nice. Our offices are close by this point, so you can also swim in summer. Right now it's really cold compared to here. And Trieste and STP is really well known for the mission with developing countries. That's why also I'm here. And you can see here a couple of examples. On the left, you see a picture of the diploma students. This is a program that we have for students from only developing countries. From this year with Mateo Civic. These are my students that should be now online following this lecture. And the example on the right is a school that we just ran in September in Serbia. It had a similar spirit as this one, also for PhDs and masters. All right, and the last slide, the publicity, is about stochastic thermodynamics in ISTP. This is a bit what we do, what my group does within the quantitative life science section. So we investigate theory and simulation mostly on stochastic thermodynamics, different topics, in the interface with biophysics, with active matter. We use a lot of martingales, like the review Abhishek was introducing today, random walks, and we try always to be in between the theory and experiments. We have many collaborations with different labs, in soft matter, biophysics, etc., even condensed matter. Okay, so as a bit of a recap of stochastic thermodynamics, I will try to show you something that was a bit surprising to me, but was maybe the first appearance of an idea of stochastic thermodynamics, which comes back to Maxwell. So you read here in Maxwell's, this is the letter of Maxwell to his relative of him, in which he was discussing about the second law that has a statistical and not a mathematical truth, because it depends on the fact that the bodies we deal consists of millions of molecules, and he was saying also that the second law is continuously being violated. Continuously. This is 1878. And that to a considerable extent in any sufficiently small group of molecules belonging to real bodies. So he was already thinking of the statistical nature of the second law, and that we could even have negative entropy, as Luca and Abhishek were introducing today. But of course, one thing is the theory. It was very well introduced today. another thing is to go to experiments and to real systems where these principles are valid and where we can see negative entropy, where we can see fluctuation theorems. A very important example is what Luca Peretti just described, which are molecular motors. My lectures will also discuss why molecular motors are paradigmatic examples of a small system that is out of equilibrium, that dissipates heat, and where we can use these principles to understand new concepts such as the efficiency of the motor, mental bounds, etc. But this is not the only class of models where we can apply the formalism. Also, colloidal heat engines are excellent model systems. There is a colloid in a trap in which we can manipulate the trap and do non-equilibrium protocols, which I will explain in detail today. My talk is about this class of systems, but also if you work in even quantum and condensed matter systems like nanoelectronic devices, you can also apply stochastic thermodynamics. So it's really a flexible framework that has had fruitful applications and still goes on. This is just to give you a smell of an idea of what's going on. Today, Abhishek was explaining about Brownian motion and that you can see Brownian motion in some situations. And this is actually not a movie done with a computer, but this is a real experiment where you pick a Brownian particle. This is a microscopic sphere of polystyrene, like plastic, in water, trapped with a laser, where you can see the motion of this sphere is kind of random. So even though it's trapped, the motion is sort of unpredictable, and you realize that fluctuations are intrinsic and you cannot avoid them anyway when you have enough resolution to see the motion of these systems. In a lab, in an experiment, you track, for example, the center of mass motion of this particle, and you will see this type of trajectory. You would like to ask what is the heat, what is the work done along one of these trajectories, and now you can go to the lab and apply what was explained today in the lecture of Abhishek and Luca. Okay? But this is a real experiment, this is real life, so we are physicists, we are not only thinking about abstract concept, but we try to understand nature. And what are these optical tweezers? It's really an important experimental setup. I think the experimental colloquia on Thursday will discuss about this, so I will give a very brief introduction. So optical tweezers were introduced by Arthur Askin, for which he got the Physics Nobel Prize in 2018, at the age of, I think, 93. And they are based on confining light in a small region in space, as I showed here on the left side of the slide. And this may sound a bit strange to you, because you say we are holding matter with light. We are taking light, and you use this light to pick a particle and to trap it in space. But you have to realize that light has energy and momentum. Momentum is energy. And this momentum can be used to push a particle against the gravitational forces of others. And this was really the concept of optical tweezers. Okay, you see here, example, it's another example, not totally related to optical tweezers, but for the photoelectric effect, you see that light can use momentum and it's transformed into energy, into electrical energy. So it's really powerful. And if you want a very good analogy with someone real or more down-to-earth example, there's this tradition in Barcelona called Locum Bala, in which they take an egg, they empty the egg, and they put a fountain of water. The fountain of water is pushing the egg and holding it against the gravity. This is really, really beautiful. And here you see that this is a balance between two forces, the gravitational force and then the force that the water is pushing the egg upwards. So the balance between these two forces produces that the egg, because the egg is moving, it's not steady, can be held in air. Optical tweezers work similarly. Here is a bit of an idea, so it can be explained a bit with ray optics. So you take a laser and you confine it with a high numerical aperture microscope. You confine the laser in a point, and then you have the opposite lens that diverts the rays, and this creates a force that is called the gradient force that pushes in the opposite direction to the scattering force that is hitting the particle. This creates a three-dimensional trap that in good approximation can be described by Hooke's law. So the force acting on the center of mass of the particle in many experiments have been checked that follow this type of equation in which x is the instantaneous position of the center of mass of the particle, x0 is the center of the trap, and kappa, we call it the stiffness of the trap. Okay? You can think about this like, please.
On the horizontal direction, is there an unstable equilibrium in this sort of?
No, it's not unstable. No. May seem that it's not unstable. It generates a cage. It's not the only way to generate a trap. You can also have two incident lights, one against the other. But this is one way in which you can do with ray optics, simple ray optics. I will need to do it sometimes, so it's like I can give you a good reference, but let me explain this. And it's not unstable. It's a stable. In the end, it works like a harmonic potential. In one dimension, the motion of the particle is similar to the motion of a Brownian particle in a harmonic well, in which there are thermal fluctuations because the particle is in water or in the fluid, so it moves, it has Brownian diffusion. The interesting thing of this experimental setup is that you can control, there are two parameters, at least two parameters that you can control. One is the stiffness of the trap, because you can make the laser stronger, so you confine, put more range here, so then this makes the trap more confined. And you can also change the center of the trap. You can drag the particle from right to left or whatever you want. So these are two possibilities, these are two possibilities of protocols, like this lambda t that Abhishek and Luca was talking about. The lambda t could be kappa of t, or could be x0 of t. It could be both. So in principle, you can do this in the lab. You can do this, please.
So what is happening is that you are trapping a particle with the help of photons, which is bombarding these particles.
Yes, photons are constantly bombarding particles, yes. Yes. So there is one force, there is scattering force, photons pushing, and the other is called gradient force, which is due to the fact that you have these inhomogeneous patterns of light. But that's more complicated to explain with a few slides. It's called my scattering and very advanced, but I can give you a reference where they explain with simple ray optics why there is this force against the scattering force. So the balance in between. Okay.
And
Please.
this harmonic representation is an effective sort of concept, right?
Yes.
So is the kappa also a stochastic variable in addition to the x?
You can make the kappa stochastic because you could have a.
I'm not asking to tune the laser power. For a fixed laser power, is kappa still?
Yeah, of course there are fluctuations, but typically, for simplicity, one assumes that kappa is fixed if you don't change the laser power. There are laser power fluctuations, but they are small in comparison to the Brownian fluctuations. So typically we neglect this, but you have to be careful with the laser power, the amplitude fluctuations as well. But typically this is neglected. One can also do an experiment where externally one controls this in a stochastic manner. I will talk about something similar to the previous question. Please.
Question is on similar lines. Energy balance equation of this particular cell.
Yes.
This harmonic potential energy is coming because of photons.
Yes, it's an effective energy that the particle feeds in the trap.
So basically, it's a part of laser. I mean, effectively, laser is giving some energy to the.
Yeah, to confine the particle. Yes. Yes. Exactly. Okay. So with this type of setup, you can track thermal fluctuations, and it's an excellent system to do stochastic thermodynamics, as I will show in a moment. So we what? Please.
So here, I mean, when you say it's a Brownian particle, you can't escape it, right? So
Yeah,
it's
okay.
like
It's
bounded in some sense, right? So
It's bounded in some sense. If you didn't have the trap, you will see Brownian diffusion.
yes, at what point that breaks down, right?
Yeah. Yes.
So what if it's very far away from the center of the focal point, right? Then it's not a Brownian. It tends to go towards the center.
Yeah, okay. If you want to be very orthodox and say if Brownian is x squared equal to dt,
Yeah.
this is not having x squared equal to dt. different. It's an orthogonal process.
So at very last time,
Yeah.
it's not grounded. That's
The equation of motion for x is an orthogonal process. So along the x dimension, you will have v dot friction coefficient equals minus kappa x minus x0 plus thermal noise. This is the equation of motion. Brownian motion is this equal to 0. Okay. In the end, it's not Ornstein. Ornstein. It's a whole Ornstein process.
So MSD will grow and then it will saturate.
Yes.
Grow and then it saturate.
Yes, actually it's very easy to show that if you do the power spectrum density, so you do x Fourier transform mod squared versus omega, you will have something like this. You will have a tail omega minus 2, and then you will start seeing, actually this is called the corner frequency, which is kappa, is around kappa divided by gamma. So at lower frequencies you will see, if you track the motion at low frequencies, which is large times, you will see it's not really visible. It's confined. Whereas if you have this equal to 0, the power spectrum will be like this. Okay. This is the typical analysis of experimental experiment. Another thing is that if you had Brownian motion, it will be like this. Really deep. In this case, because there is the trap, you will not have this. It's not, if you want to be orthodox, it's not Brownian motion.
So at small times it's fine, but at larger times it's not.
Yes, you will see the trap. You will see the trap at that time. Is it clear?
And also if I go a little bit higher side of the potential, then the potential has to also saturate. So there is some kind of, so it is not fully harmonic as well.
Yeah, as I said, this is a good approximation, close to the center of the potential. And for example, if you put two potentials and you switch them, you switch off one, you switch on the other, you will see Kramer's transitions. And you cannot have Kramer's transitions with two parabolas. You need a nonlinear path. So if you go very, very far to the trap, you will see, okay, typically we are here. But if you go very far, you will start to see that the trap is not perfectly harmonic. This depends a lot on your trap stiffness and your laser intensity, etc. There is an approximation, but it's a good approximation for many experiments, especially if the stiffness is strong, which is many in the case. Okay, one question, please.
So, can we like using the tweezers, can we have like different forms of potentials and see that how this like?
Yes, well, it depends on which type of tweezer. This is called optical tweezer, where you focus a light, focus a laser. But there's another type of setup which is called feedback traps, which, as the word says, is feedback. So what they do is they watch where is the particle, and then they have a computer that tells that controls an electrical field, and it gives the intensity of the electrical field using feedback. So if you want to build a potential that is like this, what it does is, okay, the particle is, you measure the particle position here, and then you go to the computer tells, okay, now here the force should be the slope of this potential. It's called feedback. It's a feedback loop in a setup called feedback traps. You can see a very good review by John Recoffler. Okay, with this setup, you can build almost any potential you want, square, box, whatever. Optical tweezers generally have a limitation, which is shape is typically fixed. But you could, with this, for example, do a double weld. This is easier. And not strange shape like this. This is more complicated. These are traps. Okay, maybe for the sake of time, later you can make it. Otherwise, I don't pass this slide. If there are other questions for this slide, but I'm very happy to discuss with you. Good? Okay. Okay. Let me try to go forward because I have many slides. Let's see how far we go. So what can we do with this? I think this goes directly to your question, okay? So we can, as I said, you can change the stiffness. You can also move particles. So you could have a trap in which the center of mass moves into doing circles. But you can also do something like this that I show on the right, which is to have thermal transitions. So you can create a double weld and watch when the particle jumps from one well to another, and then change the temperature of the bath and see that, of a sudden magic, the particle is jumping between two sides faster. And this is quite easy to do. You just need to heat up the water. And of course, we need the right amount of laser power, etc. Months of calibration. But then, an important question would be, apart from doing this type of academic problems, can we build this type of this movie, small like nano machines? Can we build nano engines? This is what I'll try to discuss, and also Arnav in his lecture will explain a bit about this. So what is a colloidal heat engine? So first, what is a heat engine? A heat engine is a machine that is in contact with two thermal baths. One of them is hot and the other is cold. And as a result, it allows you to extract work. You see here, two pistons connected to a wheel. Here we're heating from one side, and this heating is dissipated heat to a hot bath. Part of this energy is dissipated to a cold bath, but the other part is used as, to move a wheel. The idea of a colloidal heat engine is to do this at the microscopic scale, in which the energy or the work extracted per cycle is not of the order of joules, as we have, for example, in a macroscopic in the engine of a car, but it's of the order of kVt. So the energy that you extract in a single cycle of these small machines would be comparable to the energy of a single thermal fluctuation. So a single water molecule hitting this engine will perturb its performance. This is a bit the idea. And there have been many studies. We had a review some years ago in which we tried to rationalize all the different proposals. Here you have a simple classification of these colloidal machines. You see that you can classify in many ways, but the way we tried to rationalize was the following, that you can have a colloidal machine in an isothermal bath or in a non-isothermal environment. Remember, for a heat engine, you need non-isothermal conditions, so I'm talking about this. But also the bath could be the so-called passive bath, like having it in water or fluid, or it can be also active in the sense that it's made of biological systems that are of the size of the particle and will change the performance of the engine. This is an experiment actually done in India, and I think that one of the main authors will talk on Thursday. And I will also introduce this type of idea. Okay, so I will talk about what's happening here on the right column. Okay, before starting with colloidal heat engines, just a remark on sign convention. So the sign convention is different to the one of Abhishek and the one of Luca, so be aware. But the only thing you have to keep in mind is be consistent. Either is plus Q or minus Q. Okay, that's the point. So my idea is we have a system and an environment. There is an external agent that can either do work or extract work from the system. In this case, my convention is whatever energy enters the system is positive. So we say W is positive when we do work on the system, so when we compress it. And it's negative when the system is expanded and we extract energy from it. And the same with the heat. So the energy of the system increases when the heat enters the system. Okay? So Q, for me, is the heat absorbed by the system. Okay? It's positive if the system absorbs heat from the environment. And in this way, the energy is very simple, because if heat is absorbed, the energy increases in the system. No? So it's Q plus W. For me, this is my logic. Maybe it's too simple. Okay, so I just use this. I will use this concept for everyone. So the formulas are the same as what you saw this morning, but there is a plus Q here. The second note, the same thing. I don't use the delta. I won't explain the reason now, but I can tell you later if you want. In the total entropy change, this is the environment entropy change, this is the system entropy change. And for me, the environment entropy change is minus the heat level in the temperature. And the second law, in average, will look like this. Total entropy in average is equal to 0, which will mean that the heat will be negative. Okay? Negative means it will be dissipated to the matter. Okay? This is the most common phenomenon. So let me now try to apply this concept of first classical thermodynamics to heat engines, like the engine of a Ferrari that I showed there, or which is the same as this sketch. Okay? So in a heat engine is a machine that absorbs heat, so QH is positive from a hot bath. It dissipates heat to a cold bath, so QC is negative. And as a result, it extracts work. And you see, with arrows, it's very simple. So there is energy entering here, part of it comes here, and part of it comes here. Okay? And you see that as a result, you extract work. Okay. You need to absorb heat from a hot bath, and part of it is delivered as work. When you apply the first law in a cycle, so we think of an engine, a machine that operates cyclically, the energy change in the cycle is 0. And now you use the first law, Q plus W equal to 0. No? But there are two Q's, because there are two paths. QH plus QC plus W is equal to 0. This is the first law for heat engines in classical thermodynamics. It means that if I move the work to the right, I get that the extracted work, which is minus W, is QH plus QC. Very, very simple. There's nothing you learn from this slide. Okay? So what about the second law? The second law works as follows. We need to write this entropy production in a cycle. So in a cycle, system entropy doesn't change. Again, I'm not in stochastic thermodynamics yet. I'm in classical thermodynamics. They're not. So this is state function. My initial and the final state are equal. Delta is 0. So then I only have these two with a minus. This is the environmental entropy change in the hot bath, and this is the entropy change in the cold bath. Each of them have different temperature. And now what I do is I use the first law in this equation. So I plug in this equation here. So I kill, I think, one of them, QC. Okay? And I get this inequality, because the second law is an inequality.
Please, why delta S was 0?
Because we are doing a cycle, and delta S, the system entropy, is a state function. Okay? So the system entropy change between time 0 and time t is the system entropy at time t minus system entropy at time c. It's not path dependent. So in a cycle, I return to the same place. This is it. Okay? So I get these two. And the second law tells me that the sum of these terms is positive. Now what I do is I use the first law I just showed in the previous slide, and I get this inequality. And this inequality tells me that the amount of work I extract per heat absorbed from the hot bath is bounded by this quantity, which is independent on the details of the engine. It's dependent only on the temperatures. What I have on the left is called efficiency, and what I have on the right is called Carnot efficiency. So this is the efficiency of a cycle of a classical engine, how much work I extract from all the energy that I receive from the hot bath. The efficiency. And this is the so-called Carnot efficiency. This is a universal bound for any engine at the macroscopic scale. So the efficiency of a Ferrari cannot be better than the Carnot efficiency. Okay. This is well known. And of course, the engine that has the highest efficiency, this is something you can read from here. To get efficiency equal to Carnot, you need that this inequality becomes an equality. For this inequality to become an equality, you need that the total entropy change is 0. So you need a process of this so-called quasi-static, or a process that has no total entropy change. It's called reversible process. So when you have a reversible process, you can show that that's the optimal protocol that reaches Carnot efficiency and has this type of behavior in the PV plane. When you think about a gas that is compressed in the pressure volume space, it has two isothermals, two adiabatics, and this is how it looks, the operation of the engine in the TS diagram. You know, the TS diagram is the temperature versus the entropy. Okay? Very important is to notice that there are two lines here, these two, that are vertical in the axis of the entropy. These are called the isoentropic or adiabatic. Along these lines, this was proposed by Carnot. Along these lines, what happens is that the system entropy doesn't change. You're going infinitely slow to reach Carnot efficiency. Not only the system entropy doesn't change, but also there's no heat exchange. So Carnot, what he said in his master thesis actually, is that you need, for these two steps, these are called adiabatic, which means you need that the system or the engine does not exchange heat with any of the environment. So this is called adiabatic. It means you isolate the engine from the environment. That's the only way in a classical engine you get this type of behavior. Okay. So this is a bit mysterious to think. No? So you have the engine of a Ferrari, you have one part of the cycle you are expanding, and then all of a sudden you have to isolate it. Okay? And then you compress, and then you put it in a cold bath, you expand, and then you have to isolate it. So you may think if this is possible, if this makes sense for me. So what I will show in this talk is that This is easier to do at smaller scales than at large scales. Okay? This is a universal bound, but it's very complicated to realize experimentally, to isolate an engine from the entire universe. Okay. Actually, what many power plants and engineers are more worried about is not about being efficient, but about obtaining what is the efficiency at the maximum power. So you want that your car is fast and is powerful. So you would like that at the maximum power, the car is efficient. And this is a parameter that engineers like much more than what we do in thermodynamics. And this is a classic calculation on what is the efficiency at the maximum power. So what is the efficiency of the engine for the parameter values at which it obtains the maximum efficiency. Remember, at Carnot efficiency, you need, in the Carnot cycle, what you need to do is to drive the cycle infinitely slow. So if you do something infinitely slow, it means the cycle time is infinite. So the work done divided by the cycle time is zero. So the efficiency of the Carnot engine, the classical Carnot engine, is zero. So not the efficiency, the power is zero. So you would like to reach maximum power, and the efficiency of maximum power turns out to be related to this 1 minus square root of Tc over Th, which is smaller, of course, than Carnot efficiency. And it has been shown that many power plants follow this behavior at the maximum power. So it's quite of an accepted result in the engineering community.
What does NC stand for?
Novikov, Kurston, Argon.
Oh,
Okay? There are different
the name of
researchers who found the same result for endo-reversible engines. In most of the literature, you will see only the two last names. And in the rest of the literature, you will see only the first. So I try to use the three. In this paper, you find a couple of derivations. Okay, so now let me go to the central topic of this talk, which are colloidal heat engines. The colloidal heat engines are nothing but a miniaturization of classical heat engine, different types. So there have been experiments which seem like a Stirling engine, other experiments that seem like mimic a steam engine, like the one in all the trains, other experiments that are more fancy or new that do like a heat engine with bacteria, like using like bioenergy in a way. No? Something very interesting is the analogies here, because in a car, the working substance, so what you are compressing expanding, is the fuel. So now what is the fuel? The fuel, for example, in this colloidal heat engines, is a particle. It's a very small thing. What is the piston? The piston is the trap, because you can control experimentally how stiff or weak is the trap. So this is a sort of effective volume for the particle. So you can do the one-to-one analysis of many of the parameters in these systems. And of course, there is a temperature, which in this case will be the same. Right, so let me just try to do an overview of what has been done in literature, and I will also explain what we did some years ago. The first experiment along these lines was this one done in Germany by Bessinger lab, in which what they did was the so-called colloidal Stirling engine. So the Stirling engine is similar to Carnot. It's a bit simpler because it's made of two isothermal expansions. Well, there's an isothermal expansion where you extract work, an isothermal compression where you do work, and these are connected by isochoric transition. And isochoric means that you don't change the volume of the system. And here the volume is, the effective volume is the strength of the trap. So in the isochoric steps, what you're doing is just changing the temperature of the bath. And the only way they could change the temperature of the bath in this experiment was to put a second laser that was heating the water. So you could have a hot water when there was this second laser, not the laser of the trap, but an external laser, this heating laser, heating the sample, and then when you switch off this laser, the bath relaxes to the previous temperature. The particle is very small, again 3 microns, and of course this has some limitations because you need, in order to heat a sample, you need relaxation time. So it has advantages because it's a real temperature, it's not an effective temperature, but it has a disadvantage that it's a bit slow. Okay? And they could track with high accuracy the work fluctuations. So here you see, it's an example of what I showed this morning, the stochastic fluctuations of the work extracted per cycle, and this is cumulative. So over many cycles, you accumulate the amount of work you extract, and you see that you are extracting work out of this operation. You can also measure the work per cycle and do histograms and check for different theorems, etc. It's really a nice setup in which you can go further and measure the power. The power in this case would be the average of the work in each cycle divided by the cycle time. In this type of experiments, you can do the cycle at different speeds. So you can divide the average of the work by the duration of the cycle and have these type of behaviors. Okay? So you see that there is an optimal value of the cycle time that gives you the maximum power. So it's very interesting. So you can start thinking about optimization of engines. And similarly with efficiency, what they found is that the slower you drive the cycle, the efficiency gets larger and larger, but never above the kernel efficiency. So they used these simple models of thermodynamics in which kappa depends cyclically on time. There is also a time-dependent temperature in a simple periodic protocol, and they could have this type of theory compared to experiments, which is, I believe, is very big. Okay. Another proposal was done.
How is the work defined in this case?
In the same way as Abhishek explained this morning. In the same way. So the work is given by, here there's no external force. So it's only a conservative force. So the work is just the integral partial t with respect to t, dt. Is evaluated for respect to lambda dot dt. So you are manipulating in time the potential. You know how the potential changes in time. You have, for example, in an expansion, the potential goes from here, okay, from this situation to this situation. So it's a time-dependent potential whose stiffness is changing in time. So you know the value of the potential at all times. And then you evaluate this potential along a stochastic trajectory. The reality is partial t with respect to t, sorry for my handwritten, but evaluated at xt t. Xt is stochastic, and then along a trajectory is stochastic.
Just one more question.
Yes, please.
So mathematically we can define this work, but would they show that you could actually get like some work out of it, like lift something?
Good point. Very, very good question. Very good question. What they can do is to measure the work done in a cycle. Then a different question is if you can extract this work to do something useful. Here, this is the work done from by the external controller on the system. The external controller is the trap, and the system is the colloidal particle. So negative work means the trap extracts work from the particle. But then the point is, if when you extract work, if you can do something with it, like lift a weight. Here you cannot, because you have a trap that is opening and closing. So you need to have like a pulley to pull something. This comes in other experiments. So they could not extract this work systematically to do like moving something or do a mechanical task. They can measure the work done in a single cycle and then cumulate it, let's say, artificially, so concatenate these values of work and see that this would extract work. This could be used to lift a weight or mask it or weight keep it per cycle. But this will come. Later I will show an example where this type of work extraction is useful and you can move things. This will come.
So technically that work is being dissipated into the cold bath, right? When the temperature is low.
Yes.
So if say you do your experiment at ice like 0 degrees, right, it should show some increase of the temperature in bath. If your bath is not big enough, right?
Yes, the problem is it's an amount of heat that is really small.
No, that I agree. Like one colloidal particle can't do much, but theoretically that's what
Theoretically, if you
is
have
happening.
1 million of them.
Correct. So
Yes.
that blue it should become redder.
Yes, indeed, yes.
So that's the work.
Yes, the point is that the blue has 10 to the 23 particles and the red is 1. So you're doing work in 1 degree freedom. And this is a challenge still. So nowadays, we expect a ridiculous amount of work.
Or if you can tie something to this colloidal particle and if I mean exactly.
This will come later. Actually, this will come later in the talk. And it's one of the big challenges of this field. So right now, these are experimental demonstrations of theoretical ideas. It's really, really at the infancy.
Where is the temperature controlling mechanism? What is playing the role of mass?
The bath is water that is around the particle, and sometimes it's colder than others. So you have actually think it's room temperature, like 20 degrees, and then you heat with a laser and you heat the water to 60 degrees. So it's the same water, but it's changing the temperature. It's not that you have the engine, you move the engine to one side, which is cold, and to another side, which is hot. No, you have the engine in a single bath, and you are changing the temperature of the bath periodically.
And you're doing it in a manner that this process is isochronous.
Yeah.
Because it has to also.
Yes, the isocores actually are very quick. So these they move very fast. So somehow the trap is fixed and they just shine a laser or switch off a laser. This is what they do in this step, in the vertical step. In the other step, temperature is fixed and they are just changing the trap speed or the intensity. This is what they do. For more details, supplement I think has all details in this paper, but as far as I understood, it's like this. Okay. Some questions? Please.
Sorry, the dimension was 2 micrometers.
This is 3 microns diameter particle.
Okay, so you don't have inertia or viscosity and you're not in
No. It's not at all, because you can do the power spectrum density and check the theory. So if you take this model, which is overdone,
your model doesn't include inertia or...
this doesn't include inertia. In this case, they didn't include inertia.
So when you're doing the experiments, you always check the Reynolds number to be...
Yeah. What typical experimenters do is they measure the power spectrum density of the position of the particle, and they check if it fits one of the theories. Come from Angelo, typically.
So you're actually doing it in water?
This is in water, but there has been other experiments in lutidine, in steel baths. This was the first, so it's the simplest. Also in vacuum. Now they are doing experiments in vacuum where they can go from the underdamped to the overdamped limit. In vacuum, you can take out the air and go to very low densities, show the flow that you see the underdamped limit. Okay.
What consists of its environment in this system?
Yes?
When you say environment,
The environment is all the rest that is not the particle. So in this case, this is
no, I mean the optical tweezer, when that light is shining, that is also the part of the environment.
that we think is the external, that we think is the potential.
So you think, but that, I mean physically, that light is also there, the trap is there, so what is happening, there is an interaction between the particle and this. So when you are saying heat, work is done, work will be done not only this thing,
Yeah.
can be done on the...
Yeah, of course, you have to connect the laser to electricity, and this is also electrical power that you're not counting in the
That is fine, but what I'm saying, like when you are saying the work is done, work is to be done on the momentum of the photon, I mean the energy can
Yes,
be
sure,
transferred
sure.
to that.
But then we will need to change the model.
Yeah.
This is future work. So by now, there are simple models, effective models for the motion of the center of mass in a bath. We use thermodynamics. Still, including the photons, it's a bit of a challenge. Yeah. But it's a good idea. It's more precise.
How is the work measured?
So you know the potential because it's harmonic. You know the stiffness is previously calibrated. So you have a potential that's in some of the steps. The xt is 1/2 kappa d x squared. So you know how this changes in time. It has been previously calibrated. So you are evaluating this potential along stochastic trajectory.
Okay, so the indication that the work is being done is seen in the experiment through the movement of the particle.
Yes. So you have strategy that you follow is the following. You have a protocol for stiffness. This is kappa t. This is T. Okay, this should be not like this. This is time. And then kappa t is periodic, so maybe it's something like this. We are doing expansion compression, increase, decrease, increase, decrease. And then along this protocol, you have fluctuations of the particle. Okay, this will be x as function of t. What you do is you are evaluating the formula that Abhishek gave this morning along these two sequences. You get, in each of these cycles, you get stochastic work that you cumulate. So this figure is cumulating. Actually, what you're getting is that the work, this is the work in the first cycle, along the trajectory, that you sum, continue summing, and you continue summing. It has fluctuations, but it has negative drift. So what you're saying is that the work from time 0 to time tau is on average negative. You're using the formula from stochastic thermodynamics, from stochastic trajectories, you average over many, and it's negative, so you say you're extracting work. This is the criteria to say. Okay. Using this formalism, we also explain this problem on experimental trajectories. Okay? So they come.
And I mean, when you have this cooling photons, cooling of radium gas for example, those are some conversation. This photons and cool the system. Basically, you extract the energy of that system.
Yeah.
This is the difference in.
Yeah, this is different because in that case you're not checking the temperature, time dependent temperature. And there are doing experiments in this line, in feedback cooling. Yeah. So there is a research line in this.
So, I mean, in your molecules and doing work, moving wire, it's surrounded by very few. So there will be fluctuations in these temperature of those molecules, right? I mean, the energy, will that play a big role?
It could be, but the laser is not shining the particle. It's not shining the browning particle. The laser is shining the entire, it's shining the sample. So you may have the particle trapped here, the trap. Actually, I haven't done this experiment, but this is what I understood from the paper. The particle in the trap, there you have an external laser pointing here and hitting the water. Wait, it's not that. Okay, maybe it generates a homogeneous temperature, but it's also very difficult to measure. Very, very. It's ongoing work for many labs. See if you can track space dependent temperatures. That are very, very difficult to sustain and to measure. But yeah, it would be nice to imagine, for example, an engine and homogeneous temperature and path. Challenge and beautiful idea. More questions? I go. Okay. How are we doing with time? Because I'm a bit worried. What's that? 1 hour and a half.
40, 45 minutes.
Okay, then. I'm in the middle of talk, more or less. Okay.
So if we have time, I can ask.
Of course.
It's like saying that if I put a ratchet and a ball around that colloidal particle, which is undergoing this cyclic process, right? Then we can make it work.
Yes.
So is it similar to like how bacteria can move this ratchet or something? I mean, although they are active engines in some sense.
Yes, so what I will show later, maybe 10 slides after, will be related to this. Okay? But there are other type of experiments where they put, for example, a ratchet wheel in a bacterial bath, and this was starting to rotate, without two heat baths, in an isothermal bath. This is a beautiful experiment. They have a ratchet wheel like this. They put it, it's a microscopic wheel. They put it in water and it's fluctuating left, right, no current. And then they put it in a bacterial bath. So this thing starts to rotate in this direction. It's called active engine.
It's somehow easier to understand it in active case, but in passive case, it's, I think, see, when you extract, here also it's extracting work from bacteria, right? So
yeah, but here, you don't need bacteria at all. You just need self-propelled particles.
Yeah, that's what I mean. Right? All self-propelled particles are like bacteria. Bacteria is also self-propelled particles.
Yes, okay.
In that sense.
You can do artificial stuff.
So I'm just saying, like, instead of this bacteria, you put your colloidal particle
And rotate,
them,
make it rotate.
not rotate, but put them in this cycle of cold and hot and undergo the Stirling, whatever, like this paper is doing.
You will see something like that. So, be patient.
No, that's fine, but I was just...
Yeah, so you will see, and actually there was this year a paper on the system of Feynman branches with similar setup. I haven't seen the details, but I think it's PRL this year, or last. Karsinski and others. It's a Chinese lab. I haven't seen the details, but it looked something along this line. But I'm going to show it somewhat related, somehow. More questions? Okay, we go on. Another example was visualization of a steam engine in the same way like the steam engine of a old train. The idea of this setup, developed in Mexico, was the following: that you have a particle, barium particle, that has magnetite, and when the particle with magnetite gets close to the focus of the optical tweezer, it creates what is called, so it increases the temperature, it's superheated, and it creates a cavitation bubble. So there is a micro explosion inside the setup, and this pushes the particle out of the focus. And then the particle feels again trapped and goes back and forth. So this paper has very beautiful movies, very beautiful movies where you can see how this works. And this is for the case of the first movie, if it works. Sorry. Let me see. First movie should be working, but it's this particle that is being pushed out, back and forth autonomously. In the second movie, the same for a bigger particle of 3 microns. You see? Okay, sorry, the movie is very bad. This was better. It was moving faster by a smaller distance, like this. Okay. It was creating this bubble, explosion, and go back, trapping, etc. And this type of engine is very nice because you get a power that is much higher. The particle displaced by a larger excursions, and it's around 10 to the 8 times larger than the colloidal steering engine. But it has a bit of a problem, so there is no modeling in this experiment, and it also induces streaming in the surrounding fluid. So here, if you want to do a good model, you cannot stick with these models. You need to also include hydrodynamic effects. So it's interesting, but also it can motivate future research of many views.
Also, large discussions will not keep that happening.
Indeed. So many challenges, but very interesting experiment. And this one was the Indian version of the steering engine, in which what they did basically was to this the lab of a suit and Ganapati. What they try to do is to repeat the same protocol I showed before on the steering engine, but instead of doing it in a bath, which is just water, they just put dirty water filled with bacteria. I believe it's E. coli. So here what you see is like the PV diagram, pressure volume in the effective variables, and what they claim is, okay, this was the cycle in the steering engine, and this is the cycle that they get. There is a much bigger cycle in the PV diagram, and if you remember from classical thermodynamics, the area inside this cycle is the work extracted on average. So they claim, okay, having bacteria is very, very beneficial because we extract in a single cycle much more energy. So quite interesting. You can see here a movie, things work. On the other part, you see this, okay, shady things in the back, there are the bacteria, and then they hit with laser, the bacteria will get a bit wild, and they kick the particle in all directions, and they repeat this cyclically many, many, many times. Again, this is a bit timing, please.
So in principle, if I put more chemoattractant, I could do the same thing without like heating up the bath?
Yes, of course. Of course. It won't be a heat engine, it would be another machine, but of course you can. You could do cycles in which instead of changing the state of the trap, you're changing the concentration of a chemical species. Food, sugar, I don't know.
What did the heating do?
Heating is a laser that hits the water.
No, but what did it achieve?
It achieved larger fluctuations in the particle. So you see from here, It's the same trap stiffness, but higher temperature. So it seems that the bacteria became a bit wider. And, okay, of course, when you heat, you do two things. First, you increase the temperature of two things. Then increase the temperature of the water, but you may change also the metabolism rate of the bacteria, and they are dividing quicker.
But here that is more important. That is important.
Actually, they don't discuss this in the paper. I think it's hidden. So they just look at the motion of the colloidal particle. This is the observable. There's a lot of hidden information. They cannot track all the bacteria. And yeah, I think it's not a simple phenomenon to understand.
Is it the metabolism were not there? Then possibly you will not see this.
So you think? So how would you interpret this result?
Yeah.
No metabolism. You think? So just the diffusion of bacteria gets flat, but also the persistence. So I don't know.
It is like chemical kinetics with temperature increase.
That's what the point of
that metabolism can like go up much higher or many
that's
other
exactly
chemical
the point I was
So possibly that is the.
I just think also on the time scales, because here the cycle time is around a second. So I don't know if this will.
This is just an effective temperature.
You do not think bacterial reservoir? So, I mean, one has to maintain the bacteria. That is also taken into account.
But this is not taken into account in the energetics. Actually, there will be the speaker, the person who did this experiment will come on Thursday. So it's an online talk. We will discuss other details. So I highly recommend it because I'm talking about the work of another group. So this is my limited knowledge about this. Okay? So I highly encourage to ask this today. It's just a motivating talk to. I hope that if there is a problem, talk to the author of Thursday. Okay, but what I understood is this is beyond the standard annual model because it has also super diffusive behavior at short time. So one has to consider and challenge different models than this one, a simple annual equation. And some of the most interesting results is that they really see that you extract much more power than in a stirring engine. Here you can see what I was telling to some of you before, is the work done in a cycle, is the stochastic work. So you see, in the first part of the cycle, you do work. So when the system is cold, so the way engines work is quite simple. When it's cold, it's better. Okay, it's better to do work when it's cold because it has less fluctuations. It costs you less energy to compress something that is cold. And when it's hot, you expand. So you take profit of the thermal fluctuations and extract more energy. So you see in the stirring engine, you have stochastic work done, and then extracted, then done, extracted. The slope of this curve is very little compared to this one. In the active heat engine, you see that in the work extraction, you have these steep jumps, which supposedly come from the heating of a bacteria in the part. Of course, they cannot see this with high resolution, but this is a bit easier. They also studied something very important that they claim that now the instantaneous distribution, even if the trap is not changing in time or the temperature, is not Gaussian. So you cannot describe with the stationary distribution of a typical annual model. There are non-Gaussian tails, and they show that the non-Gaussian part of these statistics is very important for the power, for the efficiency. So they contribute a lot. These extreme events in the energetics and the efficiency. And then there's some analysis on the effective temperature, etc., efficiency. There was a lot of controversy if this can surpass Calvin efficiency or not. Now there is a better understanding of this system. I think Anna will talk about one recent paper in PRX, which I think gave a bit of an overview and a comprehensive understanding of this experiment. But there's still a lot of research on this one. Please.
So these are non-Gaussian fluctuations and what? The jumps? Like
this is could be the jumps or could be the histogram of the particle. So this is when you fix the trap stiffness, you don't change the temperature, but you have the bacterial path. You would like to characterize the stationary distribution. Yeah. And they see the stationary distribution is not Gaussian. So it's not coming from an Optical process. The stationary distribution is Gaussian. There is a signature of something is going on there, and it's non-equilibrium. Okay? Please.
So, when Abhishek or Luca derived these fluctuation relations and so on,
Yes.
the Gaussianity came into the play into deriving these. So if you have now non-Gaussian nature of the fluctuations, do those relations still continue to hold?
Which relation exactly?
Like the delta S inequality and so on.
Fluctuation relations.
He's talking about the fluctuation relations.
Yeah, but there are many fluctuation relations.
I've only learned one which Abhishek taught me.
Okay, well,
Total enthalpy fluctuation.
total, okay. Very good. Total entropy, it depends. If you think about Jarzynski most likely will not work in this case. Actually, it doesn't work. Jarzynski didn't explain this one. This is E minus S dot times T equals to 1. Okay. But remember that S dot times T, in the way we derive, and if you think about it, forget about inner values, and if you say total entropy for me is the logarithm of the path probability, this is the trajectory, and much energy today. This is the path probability, and this is the path probability of the time reverse trajectory. Okay? When you write this equation, e to the minus this is p theta divided by p. You take out the log, you put the theta here, and you put this. Okay? E to the minus this, the average of this will be the average of this, but you average with this probability, with p of x. You have p, x0 p, trajectory, you integrate, and this is a path. Okay? Path in it. So now you keep this, and then you're integrating. Okay, this is one. Okay, this is a. So if for you the entropy reduction is the log of probability ratio, then yes, the fluctuation works. If for you the entropy reduction is heat minus system entropy, then it will not work. But there is a lot of confusion in stochastic thermodynamics in the field. For many people call this the entropy reduction. The reduction, in my opinion, is the system entropy, the system variable, and heat. And here there is a lot of heat that is under the carpet. If I measure the heat, like Abhishek was explaining today with this model, I do this force times dx, I am forgetting a big part of the heat. And this actually, I think Anna will talk about this in the last lecture, how to rationalize this. It's an advanced topic, it's very risky. But if for you, the entropy production is log of probability ratio, then yes, but this is mathematics more than physics. Okay? And what Abhishek showed today, you start from Rosen and friction and force, etc., and you reach this from basic principle. I have to be a bit careful. But I think Arnav will give you the answer to this in the last lecture thing. Without expectation. Fun question. Okay, so the rest of the talk, I will now focus more on an experiment which I was involved, which tried to show if we can reach Carnot efficiency with these machines. We tried to implement a Carnot cycle with a colloidal system, and one of our ideas that we were a bit worried was that about heating. So you can heat the particle in different ways. And the typical way is, as I show here, with a laser beam, you heat the water, and it's a slow heating, and it has a limited range, because you can heat the water until it vaporizes. So you can heat up to 100 Celsius. More than this, you cannot do it. There is a bit limited. So we thought a bit of an idea some years ago, so during the PhD, which was, what if an invisible hand picks the particle and makes it shake in the same way as if the particle would be in the hot bath? Okay? You can think about this thought experiment, because you know that if you heat a bath, what will happen is that the amplitude of this noise will increase. Because here the amplitude of this noise is 2 kBt gamma, as Abhishek showed this morning. So if I have a dynamics which makes this stochastic motion, in principle, the particles will be indistinguishable of what happens up here. Okay? And the advantage is the invisible hand can be very quick, can do Gaussian noise and can move the particle infinitely far. So in principle, I don't have temperature limits. This was a bit of an idea, a thought experiment that we realized back in 2013 in Barcelona. The setup is shown here. It's standard handmade optical tweezer setup done by Iñaki Martinez in the Dmitry Petrov lab. And the idea for a theorist, the idea is shown on the top. So you have a particle in a harmonic trap, is immersed in water, but on top of that, the particle is in a microfluidic chamber, and then here there are two aluminum foils that you can buy in the supermarket, connected to an electric field, electric voltage, that has an amplitude that we generate with a computer with Gaussian white noise. So we are feeding an electric field with a Gaussian white noise signal. So it's something that is exerting an external force, very important, it's an external force that is a Gaussian white noise. So it's like having here a second term, there is a Gaussian white noise. This was our idea. And we call it white noise technique for obvious reasons. And the effective mode is, as I said, having a second noise that is independent of the first, that has an arbitrary positive amplitude, and it has also white noise properties. So what happens if you feed a particle with this external random force? So what happens is what I show here. Again, this is the power spectrum. The noise, the curve looks flat. So it has the same energy at all frequencies. It means it's white. Of course, you cannot have a perfect white noise in the laboratory. This is up to this frequency. If I have a camera that can see very, very, very small times, maybe it can see times that are smaller even than the sampling time. So than the generation of the random numbers. If I do this, this will fall. Okay? So all noises in the end are color. Even the noise that water gives to a particle is color. But if I only look up to this frequency, then it looks flat and white. Here is the power spectrum density of the colloid, which fits to the one of our non-Stephenwolf process. And then when we add the noise, it seems that all the power spectrum is lifted up. The corner frequency doesn't change, so it means we are not changing the stiffness of the trap, but the energy at all frequencies increases. And this is the same power spectrum as if we had the particle in a hot bath.
So you now have an underdamped system?
Overdamped.
Okay.
No, sorry, okay. Sorry. It's underdamped. Okay, sorry. You can do, okay. Something very important that I would like to, it's very difficult with a small blackboard. So when you have an underdamped system, the power spectrum changes with respect to the, you have this, X dot, underdamped. Actually, it's underdamped and it's critical that it's underdamped. X plus theta. Okay, let me take by now one noise. And if you do the power spectrum, so you do X in the in this morning, it's very simple. I don't have it here, but it has something like this, 2 kBT in gamma, and then it has omega minus, okay, it has three terms. One is linear, one is quadratic, and the last, which depends on the mass, is quartic. Okay? So see, W is 4. When the mass is 0, or a lower down, this is 0. So quartic in the power spectrum density looks like this. So you have this, like this. You see first W minus 2, which is this. And the fourth order power law comes at higher frequencies. And this, in our experience, that was hard to see. That's why I don't show it there. Okay? But it is underdamped. Actually, many experiments in thermodynamics, they just say, overdamping, let's go. But you have to be very careful when you do, and you will see the reason in a couple of slides. When you do cycles in which you vary temperature, you cannot forget of the mass. You will see in a minute why. So sorry, it's underdamped, thermodynamics. And what you see is that you can map the equation on the top to this equation in which two noises are considered a single effective noise with a temperature, because they are independent, you can write it as a single noise that has a temperature that is higher than the temperature of the water.
Would you also see peak?
Peak?
Peak.
may see a peak, but m divided by omega, so much, very high frequencies. Yes. Yes. We've never seen it in this. But of course, there are biological systems that are underdamped. They follow underdamped dynamics, but you can see the peaks. I have some examples, but not in this colloidal system. It's hard to see. Very hard. Okay, please.
How do you know that the electrostatic noise would also be Gaussianly distributed?
No, because we think.
Because you
So we have the optical trap here, and here there is there are two electrodes connected to a computer, and in my computer I generate random numbers that come from a Gaussian. So I'm feeding Gaussian random numbers. If you want to feed with another type of noise, you can do.
Edgar,
please.
Your gamma is missing in the first correlation. 2 cavity gamma.
Yes, right. Thank you. Gamma is missing. There, gamma is missing, but not here.
Not here.
Yes, yes, gamma is missing. Exactly. Yes, very good.
So can we have this infinity equals 0, right? It seems like temperature is just there by chance.
By chance. We are adding. Of course.
No. I mean not the sigma noise. The ambient temperature.
Well, ambient temperature, you have a part of the water.
No, that's what I'm saying.
You could cool down water to 0, and then what's the point? We have stochastic thermodynamics anymore.
No, but you have stochasticity to external noise.
Yeah, sure. Okay, yes. In this case, yes. You could have seen that.
So it's just adding something to that.
Yes. But something you may not have realized is that the field is applied in the x direction. So in the y, I'm not doing anything. So then this is a bit of a swing.
We can do like both ways as well, like
maybe yes.
Clever.
It is 2013, so the technology is. I think now, of course, yes, very good point. And actually, this comes to my next slide. You see that when you fill this on, the stationary distribution gets broader, Gaussian. And the temperature alone, okay, we define the temperature in this way, like an effective temperature satisfying equipartition theorem. If you do this with x squared or y squared, you get different results. In x, the temperature is increasing with the noise intensity, and in y, the temperature is always 300 Kelvin. So it's hitting only the x degree of freedom. Moreover, you could be worried that maybe you are generating torques and the particle rotates. We could also test this, and there was no issue with torques. But it's an inhomogeneous temperature. So if we do stochastic thermodynamics, we should do stochastic thermodynamics along the x-axis. Okay? And to give you an idea, the temperature of the sun is 5,000, the temperature of our water is 300 Kelvin, so we are in between. No? So we are going to temperatures that, okay, I remember my supervisor back then, immediately dropped. We asked him one day in the lab, how far we go with this setup? So what is the maximum temperature? And he said, as maximum as you can until the lab starts burning. Just because, and I tell you the reason, because back then, and also right now here, there's a lot of researchers that are trying to cool down particles. But our idea here is to go in the totally opposite direction, just to heat as much as possible. Of course, you will reach a moment where the particle will get trapped. So you have some limits. Okay.
Practically, the framework of this model where you have a trap where you can control the noise. So basically, you can also introduce like notion of something like active noise, which like violates fluctuation dissipation.
Actually,
here experiments can be.
Here in essence, but it's based on, okay, there is a path that was made for the dissipation. This is a second path. It's not related to the friction.
Yeah, it is also valid.
Yeah, so it's an effective.
But this temperature is not real temperature.
Yes, fluctuations, besides fluctuations.
Yeah, but the effective temperature is not real temperature, which you can measure with X.
Yeah, but if you do fluctuation response, you will get that temperature.
Okay, I can just.
Yeah, so it's not that we stopped here. So we try to see, this is in equilibrium, the equilibrium histograms look like if you're keeping this thing hot. But you have to go non-equilibrium and see if this temperature makes sense out of equilibrium. And what we did, I think Abhishek will explain you this tomorrow. This is called the Crookes fluctuation theorem that works if you are in a equilibrium bath with temperature T. But here we could check this fluctuation theorem experimentally at the temperature that is the same as the equilibrium effective temperature. So we had also non-equilibrium measurements for this temperature. There was another way which you can also measure the first passage time between two wells and define the temperature in there, and it gave the same result. So we really try to see that this works in many directions. Please.
Just trying to connect those problems with active invariant system. So there the artificial noise was provided by the bacteria. Right?
Yes.
And if we know the underlying noise
Yes,
spectrum of the bacteria, you can just plug in the same signal through your electric field, right? And maybe try to reproduce it.
Yeah. Actually, our crazy first idea was to try with other spectra of the noise, not white necessarily. Yeah. But then we got excited with white because of doing an engine. We said, okay, we can do a thermal bath, etc. But I mean, one could think of different spectra of the noise. It would be a very beautiful experiment. Nobody has done it. Well, nobody. There's a paper, very recent paper, where with a resistor they give Johnson-Nyquist noise, which is a positive Nuremberg noise. But very, very recent. 2022. So it's very, 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 very. Go on. Okay, so a very nice application of being able to control the noise is that you can design thermodynamic protocols. So before I told you that doing isothermal compressions is very simple. You don't need to change temperature, you just increase the laser intensity, and it's equivalent to compressing a gas, a one molecule gas. Now, with the technique I just explained, one can connect the external noise to the system, and this will be equivalent, if you don't change the size of the trap, will be equivalent of heating a gas, one molecule gas, in a fixed volume. So this is similar to isochoric heating. Okay. But now it comes a bit of a tricky question, which is how to do an adiabatic process. So I told you for reaching Carnot efficiency, you have to do an adiabatic process. And following Carnot, adiabatic means no heat exchange. Now the question is, can we isolate a Brownian particle? So in principle not, because there are unavoidable heat exchanges between the particle and the column, the particle and the path. So you cannot build a wall that the particle is out of the universe. This is unavoidable. So the idea that we thought about is to design a protocol in which the heat in a process, one realization is stochastic, of course, but on average, the heat is zero. So we want to find a protocol that has a distribution of heat which has zero mean. So of course, the heat in a cycle, heat Q, I call it P, but tau. This is a distribution. Okay, it could be drawn. Okay. It's a disaster. So it could be, of course, it could be Gaussian center at zero. This is one possibility. It has zero mean. And it could be also asymmetric. An asymmetric distribution which has an octave like this. So we are trying to find a protocol that has the average of the heat in the cycle time equal to 0. And this is more human, well, in principle easy to do. The theory says the following, that adiabatic plus quasi-static means isentropic. It means that the total entropy, as I said, is system plus environment. So if I do a process infinitely slow, and I want it adiabatic, so zero heat exchange, this will imply also that it's a process that is isentropic. So the system entropy along the protocol does not change. Now I have the eyes of stochastic thermodynamics, so I know what is the system entropy associated to a time t. This is the probability, the solution of the Fokker plot at time t evaluated at extremity. So I would like to find a protocol that is the following that conserves this quantity.
So this means a single cycle may not be adiabatic, but if you have to take many cycles and sum them,
yeah. A single cycle will not be adiabatic. It's not possible. It's not possible unless you have a flat distribution. That log of p is flat. So if you're in a ring, for example. But we are in a harmonic trap. That's not a ring. That's the trick, to find a protocol that conserves the average entropy at how to do this experimentally and theoretically is a challenge.
So is this idea is also similar to this tool thing, the adiabatic shortcuts?
No, shortcuts are adiabatic is different. It's totally idea. It comes from quantum and it's a different idea. Shortcuts is a beautiful name. It's not a story. This is related in quantum, I believe, to something called squeeze states. In the other section. Okay, it's not my central domain of economics, so I just explain this simple idea. So, the assumption we do is that this is a slow cycle. So at all times, we follow a sort of closed equilibrium distribution, where h of t is the Hamiltonian at time t. So this includes the kinetic part, mv squared 2, and also the potential. And then I would say, with this distribution, which I know is a big Gaussian distribution, it's a two-valued Gaussian, because it's Gaussian in V and Gaussian in X. Okay? If I compute the log of this P and I average, it turns out that the average system entropy at time T is related to the, it's like the size of an ellipse. So it's the average of X squared and the average of P squared. Is this plot? Okay? Now, if you say, I drive the system very slowly, I have a equipartition theorem. So X squared is divided by, is related to KBT over kappa. This is the, this comes from equipartition theorem on the potential energy. And this comes from equipartition theorem on kinetic energy. So you see that X squared divided by times V squared is T squared divided by kappa. So if you want to conserve system entropy in an underlap cycle, you need to conserve T squared divided by kappa. So the idea is the following. What you do is you would like to conserve the full phase space density. So, for instance, if you increase kappa, you are compressing the trap. So in next you're compressing, but also in V you are compressing. Okay. So the thing is, you compressing. No. Okay. Sorry. If you compress the trap, you need to increase temperature. Okay. This is the thing. So if you double the temperature, you have. Sorry. If you double the temperature, you have to multiply the kappa by 4. So either you compress and you heat it up, or you expand and you cool it down. Here what we're doing is this. We compress and we heat it up, so the fluctuation velocity increase, or vice versa. So these have the same area in the XV space. So we are conserving the area of the phase space. Okay? This is a bit the idea. So you have to change both. But this experimental is easy. You change the temperature by changing the amplitude of the noise, and you change the radiation intensity in time. But they have to follow that T squared over kappa is constant in time. And experimentally, you see this. If you only see the X degree of freedom, and you do log of P of X without seeing the V, the entropy is not conserved in this protocol. But if you see X and V as we could in this experiment, the total entropy is constant. Okay, constant experimentally. Look, there are fluctuations there. So the experiment fluctuations are important. We cannot do it 1 million cycles like in a simulation. So it's much more fun. It's flat. Roughly flat. The fluctuations increase because we are increasing temperature as well. So it becomes harder and harder.
But in the previous slide, there's X squared average and V squared average, they are decoupled.
Yeah.
In some cases, when we simulate, we also saw XV average. And that actually rotate this ellipse, phase space ellipse a bit.
If it rotates the ellipse, there's no problem.
So there is no problem.
There's no problem. Okay. But you have to be careful of the model. If you have forces that are velocity dependent, things will change. Okay. This is a very simple model. We have mv dot. So you have this plus mv dot. You have this model. This model is really okay. So if you have a force here that depends on velocity,
then it will be coupled. So if you don't have this velocity dependent force, then transiently there is some, but then at the long time it.
Transiently, yes, but remember that I'm trying to find a protocol that works in the quantitative unit. So slow protocol. I'm saying it's very slow. So if I do the process very slow, what do I need to get zero heat on average? So there is this assumption as well. If If you're not very slow, this is better zero, and then the problem becomes more difficult. But there are models you can solve analytically. Nowadays, there are many analytically solved models where you can work this out finite times. Things have changed since 2015. So
Edgar, the fluctuations are increasing because you choose the protocol where you increase temperature and increase kappa.
Yes, in this
but
case.
if you did the reverse case, your fluctuations would actually decrease over
Yes,
time.
yes.
And that would be a better adabaticity in some sense, or?
Yes, but remember in a cycle you need compression and expansion, heating and cooling, so you need both. If you want to do Carnot, you need an expansion, heating, and a compression, cooling. And look, when you expand and heat, the fluctuation becomes wild, or they increase. And when you compress and cool down, fluctuation reduces. So it's a bit of a trade-off in engines. So
This
you
is not one full cycle in that sense.
So it's just a microadiabatic protocol. This is not a full cycle. The full cycle we will see in a moment. It's just a process in which we are doing this from an initial to a final value. We are changing the temperature smoothly from value A to value B. We are not doing an entire cycle cooling, heating, cooling. This is just one part of the cycle.
Can you say the blue curve?
The blue curve is what a naive observer will do if you neglect the velocity. So let's say this is my underlying dynamics, but let's say okay, and I will like, okay, then I will compute. So my underlying dynamics is under down. So I have, okay, this is my underlying dynamics. But now, this generates some controversy in the field. Now I will say, okay, then, but I have of course this one, rho x v at time t. This is the solution of the Fokker Planck at time t with x and v. But now I'll say, okay, the velocity plays absolutely no role. So I will take this, integrate it out in the velocity space. Okay? And I get my marginalized density xt. Okay? And now I say, very good. For me, it doesn't matter. In the experiment, I only see x. So I will define a system entropy. System entropy for the degree of freedom x at time t. What happens? What will be this? This will be minus kb. Okay, kb, I don't know if I use it at all. This talk. Integral. Just the first example of this. Kb, the average of log of rho x. Okay. But now you only have the x degree of freedom. The other one, you have integrated out. So now, this one, if you do this, it means you take that one and you only see x, you don't see t. So you are missing this part. You're missing this part. Okay? So this, in the end, is proportional to x squared t. And x squared t, because we are going infinitely slow, with the equipartition theorem, this is proportional to t of t divided by kappa t. Okay. I'm telling you that in the protocol I'm conserving t squared over kappa, but not t over kappa. Not t over kappa. So then, if I compute this quantity as a function of time, it's not constant. Okay?
Any coarse graining reduces the entropy.
Any coarse graining reduces the total entropy. The system entropy, not the sum. Total entropy, this you will follow from Arnav, because total entropy you can write it as a Kullback glider divergence. And in a Kullback glider divergence, he will explain. Reducing degrees of freedom reduces this divergence. It's a measure of.
I was asking that because it could be either increasing also. There is no guarantee why it is increasing.
No, yeah, it could increase. You can always increase the system entropy by heating the system, because I mean, I have a glass of water made of molecules. I heat it up, the system entropy will increase because they will start moving with higher fluctuations. One thing is system entropy. One thing is total system plus environment. That one always increases. But system, you can take a balloon and compress it, and then you reduce the entropy of the system. No? 5 minutes. Now.
So this part is the adiabatic part of your cycle.
Exactly.
The equivalent
You made it very clearly. You asked me the question of the next one. Yes. So this is the adiabatic part. So the way you build a Carnot cycle is by doing a concatenation of these microadiabatic concatenated with isothermal compression response. Your total impact. And this is what we did experimentally. So we had this, see, this square dependence, because this is what makes the T-square over kappa constant. We run this over many cycles, and you can see here the Clapeyron and Carnot diagram. This is the theoretical sketch of prediction, and experimentally you get, in fact, this very nice result. So these are points that are obtained from averaging at different times along a cycle. And here there are open and closed symbols. Closed symbols is when you do the cycle very, very slowly, experimentally. And open symbols is when you do it quicker. You see, when you do it quicker, look here. So it's not a perfect square, but there are some discrepancies with the theory of Carnot. This is because we are going far from equilibrium. So you are not quasi-static, and our protocol is not anymore real adiabatic when you are very far from equilibrium. It works very well. You see the closed symbols when you drive the cycle very slow. But driving the cycle very slow means you have to be in the lab all the night, or many weeks, or many days. So it's a challenge also for a human to be doing this experiment. Okay, here just for curiosity, these are trajectories of the work in a single cycle. You see there are many fluctuations. It could be even a surprise that the average of this course is negative, but indeed it is. These are the work accumulated over many. This is the average for different cycle times. So you see that when you go very fast, you do not extract work on average. You have to run the cycle slowly. And the slower you run, you extract more work per cycle, but you take a longer time. So the work divided by the time has a trade-off. So the power is not always increasing with cycle time. This is what we see in the figure here on the right, the black one. So, okay, actually it's very confusing in the paper because it's not versus the cycle time, it's versus 1 over the cycle time. So quasi-static is here, and fast is here. So you see there is a trade-off, and there is a value which to obtain the maximum power, and very curiously, the efficiency of maximum power is the Novikov-Coulson arbor efficiency. So we verify this result. And also, interestingly, we reach almost Kernel efficiency 0.92 times plus minus 0.06. I am missing here one thing, Kernel efficiency. Okay? So we are at 0.92 Kernel efficiency, which is a very large number. But of course, we reach Kernel efficiency using one Kernel efficiency, but very slow driving. So it takes us a lot of time, suffer and effort and experiments. But it's at the expense of low power. This is a bit of a pity. But this means that Kernel efficiency can be reached in the lab, which is really nice. There are more things that are more advanced, fancy, I don't know what to say, on efficiency fluctuation, for example. So what I show here is not the efficiency over many cycles, but I compute the work extracted in few cycles divided by the heat absorbed. Okay, this is a bit notation, but the heat absorbed in 10 cycles. This is called stochastic efficiency. There are many works, theoretical works, that were done at the same time of this experiment. Also, Arnav has very beautiful papers on this topic, stochastic efficiency. And this plot is actually strange, but it tells you that the distribution of this efficiency is very broad for a small number of cycles. It gets narrower when you look at many cycles. And here it can be given by more, with a minimum. So it's really interesting. You can also see super Carnot efficiency. So short times you can have transiently efficiency above Carnot. We tested many predictions from these papers, like B-modality, super Carnot efficiencies. There are power law tails of these histograms. Okay, I won't enter, this is a bit advanced. I think Arnav will explain more. It's also a bit advanced, related to large deviations. And I will finish a bit with applications. If you give me 5 minutes, it would be nice. 2 minutes. There were many questions. So just briefly, some other applications. They build these science papers. Using this white noise technique, I could do an atom with an engine with a single atom. This is a very impressive work with an atom trapped in vacuum. I encourage you to read it. There are also, okay, this was related to your question. You can also use this work to move things. This is a case where this is called Roldan girator. So the trap, instead of being symmetric, it's asymmetric. This is an elliptic potential. Additionally, there is a torque. And then you have asymmetric temperatures, and this makes the particle rotate along Okay, so you use the work to move the particle, and okay, this is called steady state because you're not changing the temperature continuously. You have the two baths connected at all times, and it's an experiment of heat transfer. You transfer heat from the hot to the cold, always here. But okay, I will be quick. Yeah? But you can also do steady state refrigerators, which is a case where you extract heat from the cold bath and you release to the hot. So this is also ongoing research. You have a fridge. This is the fridge here. So you have a beer. You extract heat from the beer that is cold, and then you release some of this heat to the external world thanks to using electrical power. So this is the opposite. And this has been done also in small systems. There are many proposals that you can flow heat from cold to hot. For example, using Lecture-1 dynamics with non-Gaussian noises. It tells you that you need non-Gaussian fluctuations in one of the baths, and also non-harmonic interactions or potential that could be like this. When you have this, you can flow heat from cold to hot. It's a bit strange setup, but this you can realize with granular matter, for example, or maybe you could think of active matter. So this is something we speculate in the review. So maybe with bacteria in a cold bath, one could extract or design a refrigerator. This is an open question. We don't know yet, but we have this idea. Maybe someone will find it. And there were other proposals. There was an experiment by Chiliberto where he did a refrigerator also with electrical circuits. Here is a reference, so take a look. We also did, this is an article from this month. We had an idea on molecular dynamic systems where you can also flow heat from cold to hot by using what we call non-reciprocal forces. I don't have much time now, but if you're interested, you can take a look or ask me anytime. Yeah, there are many other references. You can take a look from experiments, especially. I also want to highlight some very beautiful papers done in India, for Indian stochastic thermodynamics, many years. Some of you are authors here. So very nice works. If you want the reference, I can give you later. I thank my collaborators, this experimental collaborator in theory as well. He is my supervisor. He's supervisor from Roldan. So Ignacio Martinez was meeting. Of course, we have Dimitri in our memory after all this time. And this was my collaborators in the past. And also I want to thank my group members, current members and collaborators in this project. And that's it. Thanks a lot.
So, yeah, Edgar is going to be around for the rest of the evening. And you're going to have a dinner and a week also. So, I think, so we have arranged a introductory dinner at Gulmohar Terrace. I think you all probably, you can easily find out where the Gulmohar building is.